Here's the goal. Take a bare industrial server, install SEAPATH version 2.0, tune it for real-time, and then prove it. By the end, this machine is a real-time hypervisor synchronized to the substation clock and fast and predictable enough to run protection. Not just quick on average, quick every single time, which is what protection demands. SEAPATH is the open hypervisor that runs virtual protection devices, virtual IEDs. This video is the foundation underneath them, the host. Setting up virtual IED itself comes in another video. We'll do it in 3 stages. Stage 1, on our own workstation, we build the installer and write it to a USB stick. Stage 2, at the server itself, we boot that stick and install SEAPATH onto the machine. And stage 3, back at the workstation, we connect in, tune the host for real time, and run the performance test that proves it. 3 stages: build the media, install, then tune and verify. No prior Linux needed. Every step is on screen and every command is in the description below, so don't worry about catching the exact syntax. Follow the idea here, copy the commands from there. Before any of that, let's look at the bench, because there are 2 machines in play and it matters which one we're on at each step. The first is a fanless Well-Otech R SAPC MK2, an 8-core server. This is what becomes the SEAPATH host. For the install, it has a monitor, a keyboard, and a mouse plugged straight in. That's its local console. The second is our workstation, a separate computer on the same network. Once SEAPATH is installed, the server runs headless, no screen, no keyboard, and we drive it entirely from the workstation over the network. That's how a server like this is run in practice. 2 more connections complete the picture. The server's management port carries that network link so the workstation can reach it, and a grandmaster clock, the master time source for the substation, is cabled straight into a port on the SEAPATH host. In this build, the host takes that clock signal directly. There's no switch in between. There's also a process bus network card already in the server, but it sits idle today. It belongs to the virtual IED's process bus, which will be in another video. Here we focus on setting up the host. Everything in this first stage happens on the workstation. We start by building the installer. SEAPATH publishes a ready-made installer image, the live installer with the system images bundled inside. We download it from the project's release server. Before we flash it, we verify it. You never write an unverified image to a machine you're about to trust. The project publishes a SHA-256 fingerprint of this file in its release notes, a unique signature of the exact bytes they built. So we compute the fingerprint of the file we downloaded and we compare. PowerShell does the comparison for us and returns true. The file is authentic. Now we can proceed. We unzip it to the image and write it to a USB stick with Rufus bots in DD mode. DD mode writes the image bit for bit. The ordinary mode won't boot this. You'll want a 16 GB stick or larger. One more thing before we leave the workstation, an access key. But first, what we're even doing with it. In stage 3, we reach the server from the workstation over the network to run commands on it. The tool for that is SSH, the standard way to log into Linux systems remotely. It works with a username and a password, like most logins. In SEAPATH version 1, for example, you opened a terminal and typed SSH SEAPATH at IP address. It asked for a password. Username was SEAPATH, password SEAPATH. Enter, and you're in, typing commands on the server. That's the part we're changing. A username and password like that is the weak link. It can be guessed, intercepted, or reused. So instead of a password, version 2 uses a key. And this is worth getting right, because keys come up again and again in this build. An SSH key isn't one thing, it's a matched pair, generated together. A public half and a private half. They only fit each other. Picture that password, replaced by a lock, and it's one key. The public half is the lock. You can hand it out freely, bolt it onto the server, because a lock is no use to anyone without its key. The private half is the one key that opens it, and it never leaves your machine. You don't type it, you don't send it, you don't copy it onto the server. So at login, instead of typing a password across the network, the server just checks that you're holding the key that fits the lock it's keeping, and nothing secret ever crosses the wire. There's no password to intercept or guess. That's why it's stronger, and why it's the normal way to reach a server like this. We generate the pair with one command, a modern recommended type called ed25519, very strong in a key small enough to be a single line. It writes 2 files. The private key, your one key, it never leaves this workstation, and the .pub file, the public lock the half a machine gets. We hand that public half over in stage 3 and guard the private half the whole way through. So let's actually make one. This is all in PowerShell on the workstation. One command does it, SSH keygen with 2 flags. -T sets the key type to ed25519, the modern one. Strong security in a small, fast key designed to avoid the pitfalls of the older types. -C is just a label, so you can recognize this key later. Run it, and it asks you 2 things. First, a file name. Give it something descriptive, like the one on screen, so it's easy to tell apart from any other keys. Second, a passphrase. For a lab, you can leave it blank. Just press enter. For anything real, set one. It encrypts the private key on disk. That's it. It writes the 2 files we just talked about, the private key with no extension, the half you keep, and the .pub file, the public half, the one SEAPATH gets. One more command to read the public key back so we can copy it later. It prints the public half, a single line starting with SSH-ed25519. That one line is exactly what we hand to the server in stage 3. You can also open the public key in Windows Explorer and view it in Notepad. Now we move to the server and the USB we just made. Monitor, keyboard, and mouse plugged in, and the stick in a port at the back. This is the one part we do sitting at the machine. Power it on, and as it starts, tap the delete key to enter the BY-OSS. There are 3 things to set before we install. First, virtualization. Under advanced, then CPU configuration. Enable Intel virtualization technology, that's VTX, because this host's whole job is to run virtual machines. While we're here, set hyperthreading to disabled. On a real-time host, the 2 threads sharing one physical core contend for it and inject jitter, so we give each isolated core a single dedicated thread and keep timing predictable. Then, under chipset, then system agent, enable VTDEE, the piece that lets us hand a physical device straight through to a virtual machine later. Second, secure boot. Under the security tab, turn secure boot off. The real-time kernel isn't signed by Microsoft, so with secure boot on, it simply won't start. Third, the boot order. Under the boot tab, set boot option 1 to the USB stick. Then save and exit on this board, that's F4. The machine restarts and boots into the installer. The installer is Calamares and it walks through a few screens. We set the keyboard layout. We pick the image, the DEB, E and flavor, standalone hypervisor, then the SSH key screen. And notice it offers exactly one key, the project's own default public key. That's deliberate. It's matching private half ships inside the installer, so the very first login has to use this key. There's no way to load the key we generated yet. We swap in our own in stage 3. Hold that thought. Next, the network. We need the IP address the server will use. You can set a static address yourself or find the one the DHCP server has already handed out. The link command lists the interfaces and shows which links are up. 2 of them read as up. ENP1S0 shows a carrier even though nothing's plugged in. That's the Reliant PRP card, the process bus card that later pairs with the ABB Virtual SSC600 IED. It reads up because it's a PRP red box. Its 2 ports are bridged internally by the card's own FPGA, so the host-facing link sees that internal pairing as carrier, not an external cable. We leave it alone here. ENP2S0 also shows up. That's the management port. We confirm with the address command, which gives us 192.168.0.34. The PTP clock comes later on ENP3S0. Back in the installer, we enter the IP address and the gateway. Then the one step you can't undo, choosing the disk to install onto. This machine has 2 internal drives, so before we commit, we list them and check the serial numbers on screen. SDA and SDB. SDC is just a USB stick. Since the install wipes the drive we pick, we make certain, choose SDA, and install. It runs, then asks to reboot. As it restarts, we go back into the BY-OSS with the delete key, set the boot order back to the internal drive, and pull the USB out so it boots the system we just installed, not the stick again, and we land on a login prompt that won't take a password. In version 1, SEAPATH and SEAPATH would get you in. In version 2, it won't. That's not a fault, it's the design. And it's exactly where the real work begins, logging in with the SSH keys. We move to stage 3, connect to the SEAPATH host, tune it for real time, and test it. From here on, we leave the server alone. No monitor, no keyboard. Everything happens from the workstation now, over the network. So we open a terminal there. First job, get in over SSH. The command is SSH-I, pointing at our private key, logging in as admin. The server stops us immediately. Remote host identification has changed. Before SSH even offers our key, it checks the servers. It compares the host key presented now against the one it pinned last time in known hosts. They don't match, so it assumes impersonation and refuses. That's expected. We reinstalled this machine, so it generated a new host key, and the workstation is still holding the old one. We clear the stale pin with SSH key-gen-r and the server's address. -r strips the old known host entry for that host and backs it up to known host.old. Run the same SSH-I again. This time the host is unknown, not mismatched, so SSH shows the new ed25519 fingerprint and asks whether to trust it. We answer yes, it's pinned, and the handshake continues. And here's the point, that command offered our private key with -I, yet the login still drops to admin's password. The server was never given the matching public half, so it can't accept our key and falls back to a password. That's the tell. When SSH drops to a password prompt, the server hasn't accepted your key, which is exactly the gap we close next. First, where that default key comes from, because it's the whole reason we're about to do this, it's not secret. On the release server, right next to the installer, both halves are published, the public key and the private key. Anyone can download them. So when we log in with it, pointing SSH-I at that artifact's key, we get in, but we're on a key the whole world has. We're now on the server, at its command line, on a credential anyone could hold. That has to change immediately. The lockdown is 3 moves. First, we look at what the server currently trusts. We cat the authorized keys file, and there's a detail worth showing. The default key is in there twice, listed by the installer. We'll tidy that as we go. Second, we add our own key, the public half we made back in stage 1. On the workstation we print it. On the server, one command appends it. We echo our public key onto the end of authorized keys. Then, before we remove anything, we prove the new key works. From a fresh terminal, we log in with SSH-I and our private key, and it lets us straight in, no password. That order matters. You never remove your existing way in until the new one is confirmed. Otherwise, you can lock yourself out of your own server. Third, now that our key is proven, we drop the default. We back up the file first. We copy it to authorizedkeys.back always before touching anything that controls access. Then we rewrite the trusted list to keep only our key. We grep for our key's label, write it to a new file and move it into place, which strips both copies of the default in one pass. We check with cat, one key left, ours, and the proof it worked. Our key still logs in cleanly, and the old default key pointed at with SSH-I is now refused, dropping straight to a password prompt. The machine is locked to us. A public default key is fine to get you in the door once. It's never how you leave things. Next, the web console, Cockpit. The key got us in on the command line, but the browser console is a separate door and it needs an account password, which the installer never set. So, still in our SSH session, we set 1. Sudo password admin sets the password for the admin account. It prompts twice, and that's done. Now we open a browser to the node's address on port 9090, HTTPS, the IP, :9090. The browser warns the connection isn't private. That's the console's self-signed certificate, normal for a device on your own network. We proceed through the warning and log in as admin with the password we just set. And there's the machine, a Wellatec R SAPC MK2 running DEB E and 13. Look at the system details and one line in particular. The performance profile reads none. No real-time tuning yet. Remember that word, none. That's our before. We'll come back to it. Now, one gap the installer leaves behind, and we fix it before we download anything. We try to reach the internet by name, ping github.com, and it fails. Temporary failure in name resolution. The node can't turn a name into an address because the installer never set a DNS server. Until we fix that, nothing we fetch by name, Git, the playbook, any package, will work. The fix is one small drop-in file. We create the resolver's drop-in directory with make-dir-p, then write a dns.conf into it, echo, pipe through T, setting DNS to Google's public servers, 8.8.8.8, and 8.8.4.4. We restart the resolver, system control restart, system deresolved, so it picks up the change. Ping again, and the name resolves. I'm using Google's public DNS because it works anywhere. In a real substation, you'd point this at your own. We've connected and prepped the node. Now we tune it. And we don't tune this host by hand. SEAPATH ships an ANN submodule playbook that applies every real-time setting for us. Our job in this section is just to fetch it cleanly. First, Git, the tool we'll use to download the playbook. We check, and it isn't there. Git -- version comes back. Bash git command not found. So we install it. Sudo apt update refreshes the package lists. Then sudo apt install -git pulls it in. Run git -- version again, and now it answers 2.47.3. And the fact this download worked at all is our proof the DNS fix took. Apt reached the internet by name. Before we clone, it's worth seeing what we're cloning. We open the SEAPATH ANN submodule repository on GitHub, github.com/seapath/ansible, under the official SEAPATH organization, not a fork. The green code button drops down the clone URL/seapath/ansible.git with a copy button to grab it cleanly. Now the detail that matters. Down in the file list, there's a file called .git-modules. Open it, and it lists other repositories, submodules, that this playbook depends on but keeps as separate projects. Kukin Python 3 setup, OVS, and VM manager. Notice they don't all live in the same place. Kukin sits under savoir-faire Linux, the others under SEAPATH. These aren't copies bundled in, they're pointers to separate repos. To prove it, take one VM manager and open it in a new tab. There it is, a real repository in its own right. Hold on to that, because it's the whole point of the next step. Here's the single most important command in the build. We clone the repository with git clone, but with one extra flag, --recurse submodules. Here's why it matters. Those submodules are separate repositories. The main one only points to them. Clone the ordinary way, and those pointers come down empty. And the cruel part, it throws no error. The playbook runs, it looks like it worked, and the real-time tuning silently never applied. You'd lose an hour wondering why your node isn't tuned. So, clone with --recurse submodules every time. Then we check it. We cd into the repo and ask git submodule status. And every submodule comes back filled in, each with a commit and a version, not empty. That's the trap dodged. A word first on what this section is for. Everything so far gets us to one goal, running a virtual protection relay, ABB's SSC600 ARM, as a virtual IED on this real-time hypervisor. In production, it sits alongside other virtual IEDs with a dedicated network card passed straight through to the process bus. That's the destination. But we're not installing that VM, we prepare the host to receive it. We tune its cores, its memory, and its network so that when the SSC600 arrives, the machine is ready. And all of that host configuration lives in one file, the inventory. The playbook reads that one file, the inventory, where you set the values for your own hardware. We don't write it from scratch. ABB provide an official example inventory for running the SSC600 on SEAPATH, including a README and an architecture diagram, and it's the supported, documented way, so we start from theirs. A quick look around the inventories folder shows the layout. Under providers, ABB, there's that README and the example itself. We cat the README first. It spells out what the example is for, and the files ABB ship alongside it. Then we look at the example itself. It's a YAM-UL file, and if you haven't seen one, YAM-UL is just a plain text way of writing settings, key, colon, value, with indentation showing what belongs under what. No brackets, no code, just a readable list of options. We CAD it and read the host configuration top to bottom. We don't edit ABB's file directly. We copy it to a file of our own, mynode.yaml, and edit that copy so the original stays intact as a reference. We open our copy in nah-noh, a simple terminal text editor, and work down it. A few values are obvious. We set the machine's address, its management interface, its gateway, and its DNS to ours. A few others are worth explaining as we go. Apply network config, we set this to false. Our network is already configured from the installer, and it's the very connection we're logged in over. Setting it false tells the playbook to leave the network alone, so it doesn't reconfigure the link and cut our own SSH out from under us. The PTP interface we set to the port our grandmaster clock is plugged into. We remove the parts of the example that belong to the virtual machine itself, the disk hook upload, and the pinning of the process bus card. There's no virtual IED on this host yet, so those lines would only error or do nothing. That's for another video. The Ansible user we set to admin. The playbook logs into the machine over SSH to do its work, and admin is the account that has our key and our sudo rights. That's who it logs in as. We also add one line that isn't in the example. Distribution, DEB-E- set explicitly, so the playbook definitely runs the DEB-EE-AN tuning path and doesn't skip it. Then the isolated cores. We set this to 3 to 7. A BB's design gives the virtual IED 4 cores plus one dedicated core for its emulator thread. So we isolate 5. Core 3 for the emulator, cores 4 to 7 for the machine, leaving cores 0 to 2 for the host itself. And we keep ABB's huge pages value, big blocks of memory reserved for the virtual machine, sized for the IED we'll add later. We save the file and show the finished result. Now the node is described in the inventory. Time to apply it. We don't tune this host by hand. The playbook does every real-time setting for us. LS playbooks shows the one we want, SEAPATH setup main.yaml, the host setup playbook. The tool that runs that playbook is Ansible, and the minimal image doesn't ship with it. Sudo apt install -y Ansible installs it, and Ansible --playbook version confirms it's there. Now, before we change anything on the machine, we do a dry run, because this playbook is about to touch the kernel, and we want to see what it will do before it does it. Ansible gives us 2 safe read-only modes, and we use both. First, we list every task the playbook would run. That's the --list tasks flag. Scroll up through the output and it looks alarming. Clustering, Ceph shared storage, high availability failover, dozens of plays. But here's the reassuring part. Those plays target machine groups our inventory never defines. We only declared a standalone host and a hypervisor, so every cluster, Ceph, and HA high availability play matches 0 hosts and is skipped. The list is the whole repository's menu. Our node only eats the standalone and hypervisor dishes, the kernel tuning, the huge pages, time master for the clock, libvirt. One play though deserves a closer look, the one that configures the hypervisor's network. That one does run on our node, and it contains tasks that wipe and rewrite the network configuration. Exactly what we set, apply network config to false to prevent. The catch, --list. Tasks shows every task regardless of the conditions that might skip it, so it can't tell us whether that flag actually holds. And a wrong move here cuts our own SSH, so we don't take it on faith, we move to the second mode and watch. That second mode is check mode, the --check flag, a full simulation that changes nothing on the machine. And the very first time we run it, it fails. Unreachable, host key verification failed. That failure isn't a mistake, it's the most important thing this section teaches. Here's why. Normally, Ansible runs from a separate control machine and reaches out to the node over SSH. We're doing something unusual, running it on the very node it's configuring, so the node has to SSH to itself, and that needs 2 separate things. First, it has to trust its own host key. It's never connected to itself before, so it has no record of that key. And Ansible runs non-interactively, so it can't answer the "Do you trust this host?" prompt. It just fails. Second, even once it trusts itself, the admin account has no key of its own to log in with. The installer set admin up to be logged into from outside. Our workstation key sits in its trusted list, but it never gave admin a key to reach itself. We can see both problems directly. ls-la of the .ssh folder shows the trusted keys file is there, but no private key beside it. And SSH admin at 192.168.0.34, the node connecting to itself, first asks us to trust the host key, then drops straight to a password prompt because admin has no key to present. We accept that host key once by hand. That's the first fix. It writes the key into known hosts so the non-interactive run won't trip on it, then Control-C out of the password prompt. Now the second fix, admin's own key. SSH keygen -TED 25519 generates a fresh key on the node, and note this is a different key from the workstation key we've been logging in with. It lives on the node for admin's use only. Then we cat its public half and append it to admin's own authorized keys. Now admin holds a private key whose public half it already trusts, exactly what Ansible needs to log into itself without a password. We prove it. SSH to admin now prints self SSH. Okay, straight through, no password. With that done, check mode runs clean. It works through the real tasks, detects Debian correctly, so our distribution line took effect and skips every path that isn't ours. Crucially, the cluster and Ceph plays all report, skipping, no hosts matched. And so do the network rewrite tasks we were worried about, so apply network config held and our SSH is safe. There's one failure in the output, a missing symbolic link, but that's a known check mode artifact. The real run creates the file the simulation can't. Everything that matters is good. Now we run it for real, the same Ansible playbook command, without -- check. It works through dozens of tasks and then partway through it reboots the machine to bring the new kernel command line into effect. And because Ansible is running on the box, it just rebooted, the connection drops and the run stops right there, back at our workstation prompt. That looks like a crash. It isn't, it's expected. We wait for the node to come back and reconnect with our workstation key. Catproc command line shows the first pass already did real work. The isolated cores and the performance governor are already on the kernel command line. Then we run the exact same command again. The tasks are idempo10. They check what's already done and skip it, so the second pass picks up where the reboot cut it off and finishes the remaining work, the time synchronization and the final settings. And that's the pattern to expect on a single self-managed node. It runs, reboots, and you run it once more to finish. In a cluster, Ansible runs from a separate control machine, so a reboot never kills it. Here, running on the box it configures, the rerun isn't a failure, it's just how it finishes. This is the final stretch. Stage 1, we built the install media. Stage 2, we installed SEAPATH. And Stage 3, configuring the host, came in 3 steps: connect, tune, and verify. We've connected and we've tuned. This is verify, where we prove the tuning actually took and that the machine is fit to run protection. After that final reboot, we log back in with our workstation key and check the tuning actually held, because a setting that doesn't survive a reboot is no use to us. First, the kernel command line. Catproc command line prints it and we read what's there. Our isolated cores, 3 to 7, no HZ full and RCU no CBS on the same cores, our huge pages, the performance governor, Intel P state disabled, all applied and still there after the reboot. Then we ask which tuning profile is active, tuned ADM active, and it now reads SEAPATH RT host. That none we saw in Cockpit right at the start, gone. This is a real-time machine now. Now the timing. This host is disciplined by an external grandmaster clock over PTP system control status. Time master shows the service running, and you can see it has launched the 3 pieces it orchestrates. PTP4L, the PTP engine on our timing port, PHC2sys syncing the card's clock to the system clock, and Crony D. Then we ask that engine for the state of its port, PMC get port dataset, and it reads, in capitals, slave. That's the word we want. The host is locked to the grandmaster with a path delay of just 26 nanoseconds. We also check the card itself, ETH-tool -T ENP3S0, and confirm it's doing the timestamping in hardware with its own PTP hardware clock. That's what makes the lock precise enough for protection. Timestamps in hardware, not software. Now the number that decides whether this host is fit to run protection, its worst case latency. The tool for that is cyclictest, and the first time we call it, the machine says command not found. Same story as Git, Ansible, and the playbook tools before it. The minimal image doesn't carry it. It's part of the RT test package, so we install it, sudo apt install -y RT tests, which, like every install before it, only works because of the DNS we fixed earlier, which cyclictest confirms it's now on the box. Now we run it for real, sudo cyclictest, with a handful of flags. And while it soaks, let me walk through what each flag is doing, because together they describe exactly the workload a virtual relay puts on this machine. -A 4 to 7 pins the test to cores 4 to 7, the isolated cores we set aside for the VM. We're not testing the whole processor, we're testing precisely the cores that will run protection. -T4 runs 4 test tasks, one on each of those cores. Think of each as a stand-in for a real-time function that has to act on time, every time. -P99 gives them the highest real-time priority, so nothing else on the system can push in front of them, the same priority a protection task would demand. -E200 tells each task to wake itself every 200 microseconds and check one thing. Did I wake exactly on time or a little late? That lateness, the gap between when it should have run and when it actually ran, is the latency we're measuring. -D5M keeps it doing that for 5 minutes, a proper soak, not a quick sample. And -M-H400 locks the test's memory so it can never be paged out, which would itself add delay, and tallies every result into a histogram. As it runs, it prints a live minimum, average, and maximum for each core. The minimum and average are reassuring, but the number that matters is the maximum, the single worst delay any task saw across the whole 5 minutes. For a protection-grade host, we want that worst case down in the low microseconds. While that soaks, we open a second window alongside it to watch the thermals at the same time. The tool there is turbostat, which lives in the Linux-CPU power package, so we install that too, sudo apt install -y Linux-CPU power, and run sudo turbostat -interval 5, which prints a fresh reading every 5 seconds. We bring that window full screen to read it, while cyclictest keeps soaking behind it. 3 columns tell the story. BZ_MHZ is the actual clock speed each core is running at while it's busy. We want to see it sitting at 4,004 GHz, proving the performance governor is holding the cores at full speed and not letting them idle down. Package temp is the package temperature, the temperature of the whole CPU in degrees Celsius, the headline thermal number. And package watt is how much power the processor is drawing, in watts, how hard it's actually working. Reading across those columns live, the cores are pinned at 4 GHz and the package is sitting at 57 degrees. When cyclictest finishes, we bring both windows back side by side and read the result. The worst case maximum across all 4 cores is 8 microseconds. The bar for a host like this is a worst case under 100. We came back at 8, with nothing falling outside the histogram at all, comfortably inside the window, every single cycle. That bounded, predictable latency is exactly what qualifies a host to run protection, the promise we made at the start, now proven. One more check on the thermals. A fanless box running full turbo invites one question. Did it ever quietly throttle, slow itself down to shed heat during that soak? We ask the kernel directly. Sudo d-misg piped to grep-i, thermal or throttle, searches the kernel log for any thermal or throttle message. What comes back is only boot time housekeeping, thermal monitoring enabled, the thermal zone registered at 28 degrees, all time-stamped in the first half second of startup. If the CPU had throttled under load, we'd see a temperature above threshold line stamped from during the test. There are none. So the box held 4 GHz at 57 degrees with 0 throttle events. And here's what that 4 GHz really tells us. The only speed Intel guarantees on this processor is its base, 1.5 GHz. Everything above that is turbo, which a normal power-saving system hands out only when it feels like it, and takes back the moment the machine looks idle. Now look at the requirement. A BB's SSC600 in version 1.5.1 asks for a minimum CPU frequency of 2.2 GHz, which is above this chip's guaranteed base. So on a default system, between events, these cores could legally drop to 1.5 GHz, below what the relay needs, and then have to scramble back up exactly when a fault arrives. That's the trap the tuning closes. The SEAPATH performance profile pins the cores at full speed and keeps them there, and the turbostat reading proves it held, 4 GHz, flat for the entire soak, never falling back towards that base. So the relay always has the headroom it needs, the instant it needs it. Finally, we go back to Cockpit, full screen, and look at the performance profile. At the very start, it read none. Now it reads SEAPATH RT host, the whole tuning, the core isolation, the timing, the governor, summed up in one line. One honest caveat, this is an idle host, no virtual machine, no sampled values load yet. So this is a clean baseline, not a worst case. We retest it under real load when we add the SSC600 next time. And that's the whole build, from bare metal to a fully verified real-time SEAPATH host, ready to run protection. Everything was done in the open, the real way, start to finish, so you can do the same. Every command used is in the description. In another video, we bring this host to life with its first virtual protection relay.